Okay, welcome everyone, and good evening to you. Good evening to the person who greeted me also. And thank you. I received a message from the CR, so thank you for that. Uh, I am not going to put up the slides on for any of the lectures. The slides are available on my homepage. I will only put up the video recording for the lecture and my handwritten notes in the lecture. So in any case, someone has written lecture 2 slides are not there in the drive. So I will check once again after 2. Okay, so uh, let us begin. Okay, so today's lecture will be, I think, one of the more interesting lectures in this course, although perhaps not the most interesting one. I mean, interesting to me at least. So the important things, let's quickly recap what we did so far. And I have explained this point again and again many times, so we'll be quick about this. The important things we did so far are how to compute radius of convergence of a power series. Power series defines a nice function in its interval of convergence. Suppose we are given an ordinary differential equation y double prime plus p of x y prime plus q of x y equal to 0, and p of x and q of x are analytic, which means given by a power series and in a small interval I around x naught, a point x naught. Then the solution y is also analytic on the interval I. And we can compute the two independent solutions to an ODE as above by plugging in a power series into the ODE. So we just take y of x, we assume that y of x, I mean, because of this previous point, y of x is going to be equal to summation an, let me just write this. So because of this point, y of x, we can just assume is summation n greater than or equal to 0, an x minus x naught to the power n. Okay, that's too small. Because at this point here, we can assume. Yeah, I mean, I've said this numerous times, but there's no harm in saying it once again because this is one of the most important points in this course. We can just plug this in and then we have to solve for the coefficients. And we can compute the, okay, yeah. So once we do that, we will get recursive relations for coefficients. So we will be able to find out the higher ans in terms of lower ones. And we can choose, usually we can choose A0 and A0 arbitrarily, and that will give us the solution we are looking for. Okay, so today we will do a special equation. And that's called the Legendre equation. Okay, so someone has written, sir, can you please convert the slides to handout format before uploading? So as I have told all of you, all my slides in handout format as well as in slides format are available on my homepage. So you just have to go there and you can download there. These slides were made available, I don't know, months ago. Okay, so let me go ahead. So the following differential equation is known as Legendre equation. So this differential equation is known as Legendre. So this one. So here P is a fixed real number. And by existence theorem, power series solution in X exists on the interval -1, 1. So that's because this function over here, oops, sorry. This function over here, this does not vanish at x equal to 0. And therefore we can rewrite this as y double prime minus 2x upon 1 minus x square y dash plus p into p plus 1 upon 1 minus x square into y equal to 0. And these functions are nice functions around 0. So that's why we can find a solution to this in terms of using the power series method that we learned. So, and now let's just quickly follow the steps. We put y of x equal to summation n greater than or equal to 0, an x to the power n into this equation. And then we equate the coefficient of x to the power n in the resulting equation to 0. So equating the coefficient in the resulting of x to the power n in the resulting equation to 0, we get the recursive relation. So this is the recursive relation that we get. So let's just stare at it for a few seconds. Okay, so let's go to the next page. So from this, we easily see that an plus 2 is given in terms of an. And an plus 2 is a function of an, p, and n. Okay. So let us set a0 equal to 1 and a1 equal to 0 in the recursion formula to find a first solution. So, okay, this solution that we get, we call it y1x, and we note that it is an even function because a1 is 0 and therefore all the odd coefficients are going to be 0. So therefore this function is just going to be 1 minus, okay, I don't need a a0 here because I've put a0 equal to 1, so this should not be here. And obviously this is an even function. And similarly, we can find a second solution by setting a0 equal to 1, a0 equal to 0, and a1 equal to 1 in the recursion formula. So then we get the second solution. So yeah, once again, this should not be here. And notice that this is an odd function. Okay. So let's just stare at these coefficients for a few seconds because we are going to make an observation using them. Okay. So thus the two independent solutions are. So we can, these two solutions are linearly independent. And every solution is a linear combination of these two. Okay. So here's a remark. So if P belongs to this set is this set. Then y1x is a polynomial function. So yeah. So because let's just see if P is, if P is 0, then all these coefficients are going to be 0. So if P is 0, then y1 is just the constant function. So let's see. If P is 2, then this is going to vanish and all subsequent terms will also vanish. And yeah, so similarly, if P is 4, then yeah, so and so on. So you can easily deduce this from the recursive formula. So yeah, I don't want to go back to that. And similarly, if P belongs to this set 1, 3, 5, and so on, then y2x is a polynomial. So this observation is going to be crucial. So let's go ahead. So thus, if P is an integer, then exactly one solution is a polynomial and the other is an infinite power series. So yeah. So you can just stare at it for a few seconds and convince yourself. Okay. So the general solution y of x is equal to a0 y1 x plus a1 y2 x is called a Legendre function. And if p equal to m is an integer, then precisely one of y1 or y2 is a polynomial, and it is called the mth Legendre polynomial. So and we write it p sub m x. So for m greater than or equal to 0, note that Pmx is a polynomial of degree m. It is an even function if m is even and an odd function if m is odd. So yeah, we can, I don't know, we can try to see this for first few m, maybe for small ones. So if we take m equal to 0, so we have to take m greater than or equal to 0. And we have to look at Pmx, right? So when we put m equal to 0 into this, so okay, so m is p, so yeah, okay. So m is p over here. P is equal to m. So I don't want to use, I don't want to write p sub p because then there will be too many p's. So yeah. So when we put m equal to 0, so that means we are putting p equal to 0 here. That means this is going to be 0. All these terms are going to be 0. And this is the constant polynomial as we saw before. So therefore it's correct. P0x is a polynomial of degree 0. Now let's take m equal to 1. So when we take m equal to 1, that means uh, this one is going to be an infinite power series, but this one is going to be a polynomial. So all these coefficients are going to vanish. So P1 is a polynomial of degree 1. So that's also correct. Now if we take m equal to 2, so yeah, it goes on. Yeah. So when we take m equal to 2, this one becomes an infinite series, and this one, all these terms from here on will vanish. And yeah, only this coefficient survives. So P2 of x is a polynomial of degree 2, and so on. Yeah, so these are some simple observations. So you should just look at the coefficients and convince yourself that these are true. I mean, it's going to be trivial. Okay, so let us write down few Legendre polynomials. It's just for fun. Okay. Yeah, so I have written this down. Yeah, so you can just observe that P3 is a polynomial of degree 3 and it's odd. P4 is a polynomial of degree 4, etc., etc. So the graphs of PMs in the interval -1, 1 are given below. So all this is not important. It's just for fun. We have a bunch of polynomials and we try to play around with them a bit. Okay. So let's go ahead. Yeah. So what is so interesting about the collection of Legendre polynomials? So to answer this question, we need some linear algebra. So let me begin by recalling what vector spaces are. So we recall the notion of inner product space from linear algebra. So first recall the notion of a vector space V over R. So we will concern ourselves. The underlying field is the real numbers. So a vector space is a set equipped with two operations. We have an addition. So we should be able to add two vectors. And we have scalar multiplication. So the underlying field is R. And so we should be able to multiply each vector by a scalar in the underlying field. And that should give us a new vector. And okay, and these operations, they satisfy some nice properties with nice properties, like for instance, if we add two vectors v plus w and plus, I don't know, u, this is equal to v plus w plus u, etc., etc. So yeah, a vector space has a dimension which may not be finite. So I want to emphasize that because soon we will deal with vector spaces which are infinite dimensional. So so what is an inner product space? So yeah, so please note that when we specify a vector space, there is no inner product on it a priori. The infinite series won't converge. Like, of course, the infinite series will converge in. So someone has asked a question: the infinite series won't converge. No, the infinite series will converge in the interval -1, 1, because that's what we saw, right? I mean, the polynomials. Y double prime minus 2x by 1 minus x square y prime plus p into p plus 1 by 1 minus x square into y is equal to 0. So these two functions, these two have a series. They are analytic in the, I mean, the radius of convergence is 1. So they are analytic in this interval. So yeah, so the series that we write, that will at least converge in this interval. It may converge in a larger interval. Okay, but sorry. Let me not get distracted. So, so we take a vector space V over R. So this is not necessarily finite dimensional. So a bilinear form on V is a map. So it's a map from V cross V to R. And as the name suggests, bilinear, what does it mean? So it is linear in both coordinates. So we can fix any, if we fix any W in V over here, then this gives rise to a map from V to R. after we fix this small w, and this map should be linear. And similarly, if we fix any v over here, then we get a map. So I don't know, maybe I should write this as v cross w to r. We restrict this function to v cross w to r, and that function should be linear. This function should be linear for all w. And similarly, if we fix a v, this function should be linear for all v. So anyway, the precise definition is given here. So let me say, is this? Yeah, so this is the precise definition. But I just wanted to point out that the definition is what it is suggested, I mean, what the name suggests. Okay. An inner product on V is a bilinear form on V, which is, so this is just a bilinear form, but we need this form to have some nice properties. So we need it to be symmetric. So the inner product of V and W should be equal to the inner product of W and V. And we need it to be positive definite. So which means that when we take if we take any vector V and we take the inner product of V with itself, then it is always greater than equal to 0. And it is equal to 0 only if the vector V is 0. Otherwise, it's always, if V is non-zero, then V comma V is always positive. So a vector space with an inner product is called an inner product space. Okay. What is a form? If you don't like the word form, you can use the word map. A bilinear map on V is, yeah. So, okay, so let me go ahead. So, I mean, it's just, I mean, you have to give, you want to call it something, right? So it's, yeah. So next we come to orthogonality. So in an inner product space V, two vectors u and v are orthogonal if, when we take the inner product of u and v, that becomes 0. So we roughly know what this means, right? I mean, it just means that they are perpendicular to each other. So, okay, let me not write this. So more generally, a set of vectors forms an orthogonal system if they are mutually orthogonal. So, I mean, we can just take any set of vectors, let's say v1, v2, up to vr, any vectors in V, and we say that this forms an orthogonal system if vi comma vj, the inner product is 0, okay, is delta ij. Okay, I don't want to write delta ij, is 0 if I is not equal to j. Vi comma vj. Okay, so all these definitions are fairly easy to understand, and they are what they are as the name suggests. An orthogonal basis is an orthogonal system which is also a basis. So please note that here, let me emphasize that. So a basis means that, so a set Vi, where I is in some index set. So this is a subset of V. If a set is called a basis, if the vectors in it are linearly independent. So the first condition is they should be linearly independent. So what does this mean? It means that if I have any finite relation, so let's say j equal to 1 to m, a j v I sub j. So if I have any finite relationship between these, then all the aj's are 0. And 2, they span V. So what does this mean? It means given any vector W, there exists I sub j's, Vi sub j's, such that I can write there exists an M and vi sub j's, so that w can be written as a finite. Okay, so this finiteness is very important. Every w can be written as like this. Okay, so when we use the word basis, or whenever we do linear algebra, every time we write a sum, we take a finite sum. We don't allow any kind of infinite sums the way we saw in series. So that's very important. Okay, so an orthogonal basis is an orthogonal system which is also a basis. So I emphasize this because soon we will be looking at situations where we take a vector and we write it as an infinite sum, and then we have to make sense of that. What do we mean by that? So that is what we are coming to, and therefore I thought that it is important to emphasize that every time we do a course like linear algebra, and we talk about basis, so we usually mean any kind of sums that we take, they have to be finite sums. Okay, so let me go ahead. So let's take a really simple example. So we can look at the vector space Rn with coordinate y's addition and scalar multiplication. So I mean the usual vector space Rn. So this rule is going to define an inner product on Rn. All of you know that. And the standard basis E1 through En is an orthogonal basis for Rn. So the previous example can be formulated more abstractly as follows. Okay, so this is just yeah. So we can take a finite dimensional vector space with a basis E1 through En, and we can artificially define inner product on V. So this inner product of course depends on this basis. So we define so given any vectors U and V, so since E1 through En is a basis for V, we can write U as summation AI EI, and we can write V as summation BI EI. So all this is happening over real numbers, finite dimensional vector space over R, let's say. And we define this inner product on V. So this defines an inner product on V, and with this definition, the E1 through En is an orthogonal basis of V. So this is really a stupid example. So nothing is happening here. Okay. So someone has asked this question, but won't we have infinite sum when we have an infinite dimensional space? So that's the whole point. When we talk about vector spaces, I mean, when we talk about when we say that in the two conditions which define a basis, I just wanted to emphasize that we cannot write an infinite sum. So yeah. So let me go ahead. So so suppose V is a finite dimensional inner product space, and E1 through En is an orthogonal basis. Then for any small v in capital V, any vector V, we can write the vector in this form. Okay, this is really a Mickey Mouse lemma, which all of you have seen or will probably will easily be able to prove. So let's see the proof. So since E1 through En is an orthogonal basis that's given to us, in particular it's a basis, so I can write my V as summation AI Vi, and our task is to find these AIs. So we just take the inner product. Yeah, we want to find the coefficients AJs. So take inner product of V with EJ. So when we take inner product, so because of the so yeah, so the first equality is by definition, the second is by bilinearity, and the third one is because the EIs are orthogonal. And so we get that AJ is equal to V comma EJ, the inner product of V and EJ divided by the inner product of EJ with itself. So that proves our lemma. So orthogonal basis. So here's another lemma. In a finite dimensional inner product space, there always exists an orthogonal basis. So the proof is simple. We start with any basis and modify it to an orthogonal basis by the Gram-Schmidt orthogonalization process. So if you don't remember this, today is a good time you can revise it. This result is not necessarily true in infinite dimensional inner product spaces. For infinite dimensional vector spaces, we can only talk of a maximal orthogonal set. So a subset E1, E2 dot 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 is called a maximal orthogonal set for V if Ei comma Ej is delta Ij. Okay, so this means they are mutually orthogonal, and also in addition to that, we need their norms to be one. So the norm is by, yeah. So by, I've used the word norm, but let me not define it. I suppose you guys, you know what it means. But in any case, what we, if you don't like it, so this, we just want Ei comma Ei to be one. Okay, and the second thing we want is that if V is a vector such that the inner product of V with Ei is 0 for all I, then V is 0. Okay, so let's just pause for a few seconds and stare at this slide. Okay, someone has asked a question. These EIs are the unit vectors in each direction. So now we have to be a little bit careful over here. When you use this a term like this, EIs are unit vectors in each direction, you have already assumed that your vector space is like Rn. Yeah. And I would like to warn you not to make this assumption. Now, because now if we have any finite dimensional vector space, we can always choose an isomorphism. Yeah, I mean, I can just take any basis, E1 through En for V, and I can always choose an isomorphism of V with Rn. I mean, I can just, okay, so let me call the basis Vi over here. V1 through Vn. There's any basis. So I can give an isomorphism like this from Rn to V. I just send the standard vector Ei. I just send it to Vi. Yeah. But here we have made a choice. Yeah. So, I mean, the choice of these VIs. And as you will see immediately, very soon, that there are many vector spaces where there is no natural way to choose these vectors. Yeah. In Rn, because we are familiar with Rn, we can say that, okay, there's a particularly nice choice for a basis, E1 through Ens. Yeah. So I just want to, yeah. You don't know what an isomorphism is? So someone has told me that he doesn't know the definition of an isomorphism. So an isomorphism just means a map which is one-to-one and onto. Yeah, suppose I have a map, F is a linear map between two vector spaces. I won't define a linear map of two vector spaces. Then there's something which you should know. Then F is called an isomorphism if F is 1-1 and onto. So in particular, it means that both these vector spaces V and W are the same. Yeah, because the map F, it preserves the linearity, it preserves the linear space structure, and it's both. Yeah. So as far as their vector space structure is concerned, they are the same. So I hope that clarifies. Okay, so let me go to the next slide. Can we always have a maximal orthogonal set? Yes. Yeah, but okay. Okay, so yeah, I mean, I suppose we can always do, we can always keep adding. Yeah. This, okay, let me ignore. So the answer is yes, but I don't want to, let me go on. Maybe I'll make some comments about this in the end or at the end of the course. Yeah. Okay. So, length of a vector. So this is also something which you should know, which you probably know. For a vector v in an inner product space, define the norm of v to be, we take the inner product of v with itself. So if v, so this quantity, this number is always greater than or equal to 0. So that is one of the conditions we required when we, in our definition of inner product space, and we just take the square root. So this is called the norm or length of the vector v. So all these definitions are, of course, motivated by what we know about Rn and our analysis about Rn. Yeah, but we will soon see that we can have vector spaces which are very abstract, and there is no natural way to choose a basis in them. So it satisfies the following three properties. Okay, so norm of 0 is 0, and if v is not 0, then norm v is strictly greater than 0. Norm of v plus w is less than or equal to norm v plus norm w, and norm of av is equal to absolute value of a times norm of v for all v comma w in the vector space v and scalars a in R. So let's prove Pythagoras theorem. So what does it say? It says that for orthogonal vectors v and w in any inner product space, norm square of v plus w is equal to norm v square plus norm w square. Okay. Okay. So the proof is simple. So norm square of v plus w is, by definition, inner product of v plus w with itself. And using bilinearity, we can expand this. And because v and w are orthogonal, these two are 0. These two are 0. And therefore, we are left with this. Okay. So this ends the proof. Okay. I don't understand why I've called this Pythagoras theorem, but anyway, never mind. Let's go ahead. More generally, for any orthogonal system v1 through vn, we have norm of v1 plus dot dot up to vn square is equal to norm of v1 square plus dot dot up to norm of vn square. Right. So the same proof will work. So this is also obvious. Okay. So here comes our non-trivial example, the one which I was referring to earlier. So let's look at the vector space of polynomials, right? So the set of polynomials in one variable x is a vector space. So this is obvious, and we denote this by p of x. And the set 1x x squared dot dot is an infinite basis of the vector space p of x, right? This is true, right? Because we cannot, all these are linearly independent, because I mean a0 into 1, we cannot have any relationship of the type that's a1 into x plus dot 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 plus an into xn is equal to 0. We don't, I mean, this polynomial is never going to be equal to the 0 polynomial, right? So as polynomials, these two are not the same. So obviously these are linearly independent. And once again, this, although this set is infinite, I mean, I did not check a condition of this type. ai x to the I is equal to 0 implies ai is equal to 0, right? I greater than equal to 0. So to check that these are linearly independent, this is not the condition that I checked. Yeah, I checked that any finite sum. So this is what I was trying to explain earlier. So these are linearly independent, and obviously every polynomial can be written as a linear combination of this. That's by definition. Okay, great. So this is an infinite. This is a basis for the vector space p of x, and the cardinality of this basis is infinite. Now we define an inner product on p of x. So this is a nice inner product. So given any two polynomials f and g, yeah, we just define the inner product to be this. We multiply f and g, and we integrate from -1 to 1. So what are the two conditions that we needed to check? Okay. So we are integrating over a finite interval -1, 1, which ensures that the integral is finite. Yeah, sure. So, and what are the two conditions that we needed to say that this is an inner product? We needed, we needed that f comma g is equal to g comma f, but that is obvious. That's one condition. We need it had to be symmetric. And the second condition we needed was that if f comma f should be greater than or equal to 0, and f comma f equal to 0 if and only if f is equal to 0. Right? So this is also obvious. Yeah. Okay. So this is indeed an inner product. Right. So yeah, of course. I mean, this sentence is basically saying that we are defining a map from P of x cross P of x to R. Right? Given any two polynomials, I need a real number, and for that I need to say that this integral is always going to be finite. So that is the importance of that sentence. Okay, so let's go ahead. So the norm of a polynomial is by definition f comma f, so which is this. Okay, so now let me come back to the question that was asked earlier. So earlier someone had asked that are these unit vectors in a certain direction? So the point is, like, how do you make sense of any direction in this vector space P of x? Okay, so there are no standard directions unlike in that we have in Rn. So that is the word of caution I wanted to sound. Okay. In general, you can integrate. So someone has asked a question. Okay, I'd like to request this person to ask this question publicly, because I mean, there's nothing to be. I mean, I don't have a problem if you ask me privately, but if you ask it publicly, then everyone will know your question, which is good. So in general, we can integrate over any subset of R. Well, if you integrate a polynomial over all of R, since you say any subset of R, then the number may not be finite. I mean, if you integrate x square over 0 to infinity, I mean, I suppose the area of the graph is under the graph is infinite. So this number is not going to be finite. So in the case of polynomials, you can integrate on any compact set. So you can integrate on any interval of the type a and b. But over here right now, for our purpose, we want to integrate from -1 to 1. Okay, so so someone has asked me, can you tell again what you did? I mean, that question is very vague. So if you could be more precise, then I can try to answer this question. Okay, so let me go ahead. Oops, sorry. So here is a trick which we will use again and again. So it's a stupid trick, but it's very useful. So so here we have two functions f and g. Let's say they are nice functions. They are at least once differentiable. But let's just imagine they are polynomials, which is why we are going to use it right now. So when we differentiate this, we know that this is equal to g times df by dx plus f times dg by dx. Okay, great. So now we integrate both sides. So we have integral from -1 to 1 d by dx of f times g is equal to -1 to 1 g df by dx plus -1 to 1 f dg by dx. So, and this left hand side, this is just the function f times g evaluated at 1 minus f times g evaluated at -1, which is precisely this. So okay, so now if this term is 0, yeah, so we want to, if this term on the left is 0, then we get this. Okay, so we will use this trick repeatedly. So it's called derivative transfer. So this will be used sometime later also in this course as a way to, this is just if you remember this, then it becomes a little bit faster to deal with integrals. I mean, you could always do that computation. So in our situation, what is going to happen is that this function f times g, sorry, the way we will use it is that this function f times g, this function will vanish at 1 and it will also vanish at -1. that is really going to be the way in which we are going to use this trick. So let's just see how to use it. Okay, this will be referred to as derivative transfer. Okay, so let me just this slide here. Okay, can we always write f times g1 is equal to f of g into f of 1 into g of 1? That is the definition of f times g. How do you define the product of two functions? Yeah, I mean, when I write, suppose I'm given two functions f comma g from any space x to real numbers. So the meaning of, then I can define a new function f times g. Let me call it h. H is a new function from x to r, and the definition of this function is h of x is defined to be f of x times g of x. Right, it's product, not composition. Okay. Okay, so let's go ahead. So now we want to, okay, so great. So what have we done so far? We have defined some polynomials P of x. These are the Legendre polynomials. These are polynomials for each m greater than or equal to 0. Right? So these appear as solutions to a differential equation. Not a differential equation. There are many two differential equations. For each m, there is a differential equation as solutions to differential equations. Two differential equations. Right? For each m greater than or equal to 0, we have the Legendre equation. And one of the solutions of that Legendre equation is this polynomial, which is Pmx. And we saw some properties of these polynomials. And now we are going to prove some very nice properties of these polynomials. So let's go ahead. So since Pmx is a polynomial of degree m, it follows that P0, P1, P2 dot dot is a basis of the vector space of polynomials P of x. So this, I will leave it to you as an interesting exercise. Yeah, so you should try this exercise. And yeah, so this, let me just write left as exercise. Left as, it's an easy exercise, but it's a little bit interesting. Okay. Now the theorem which we are going to prove is, if, and I hope you guys find this theorem interesting, because it's kind of nice that, okay, we have these differential equations and we picked up some solutions of these differential equations, and lo behold, these solutions, they turn out to be orthogonal to each other with respect to this inner product that we put on our vector space, so which is the vector space of polynomials. Okay, so so let's just stare at the theorem for a few minutes. Let's understand what this is. So it says, so this is, so on Pmx, on not P, on P of x, we have the inner product, which we defined in the previous slide, which is precisely given by this. And with respect to this inner product, when we take the inner product of Pm and Pn, it is 0 if m is not equal to n. And if m is equal to n, then this is 2 upon 2n plus 1. So that is, the Legendre polynomials form an orthogonal basis for the vector space P of x. Right? So it is a basis already. So that is because of this exercise. That is because of this exercise, which you should do. And we will also be proving that they are orthogonal to each other. And not only that, this theorem states something more. We even know the norm. We even know the norm square of each of these. Yeah, exactly. Okay, great. So let's see how to prove this. So I hope the statement of the theorem is clear to everyone. Okay, so let's go ahead with the proof. So the Legendre equation may be written as 1 minus x square into y prime. So when we look at this, when we take the derivative of this, this is, so this is just d by dx of 1 minus x square into y dash, which is equal to, so, okay, so 1 minus x square into y double dash minus 2x y dash. Right? So this is exactly the Legendre equation for P. And in particular, Pmx, since it satisfies the Legendre equation, for m, for p equal to m, it satisfies this equation. Yeah, here I have put p equal to m. Okay. So we multiply this equation star with Pn. So this equation, I multiply this with Pn and I integrate, right? So I get exactly this. Right. So this is immediate. And now we apply derivative transfer. So let's look at this function f, right? So what did derivative transfer say? So it says that, so we needed fg of 1. Okay, so minus fg of minus 1. So let me put it from like this. Sorry. So derivative transfer says that if fg of 1 minus fg of minus 1 is equal to 0, which is going to happen if both these are individually 0, then this will obviously happen. Then integral f dg by dx is equal to minus integral g df by dx. Okay, so we are going to use this repeatedly. So here we are going to take f to be this thing, right, and g to be Pn. Now notice that f of 0, I'm sorry, f of 1 and minus 1 are 0. So obviously, and this term over here, this was by definition f of 1 into g of 1. So obviously both these terms, this term as well as this term, both these terms are 0. So therefore we can apply derivative transfer. So what do we get? So this is integral f dash g. So we just have to put a minus sign and this becomes f g dash, which is exactly what we have. Okay. So let's go ahead. So now we interchange the roles of m and n. So this stuff, so we got this equation. So let me erase this right now. Let me erase this. Now that we understand it, we got this equation. And this holds for any m and n. So we can replace the roles of m and n, right? So then we will get minus of, minus 1 to 1, 1 minus x squared pm dash pn dash plus n into n plus 1 integral this thing is 0, right? So subtracting the two sides, yeah, so notice that, so this equation tells us that this object is equal to minus of this object, right? And the next equation is saying that this object, which is the same as the first term in the previous slide, is equal to this thing. So which means that we have this, right? Subtracting this, we have this. Yeah. But obviously, if m is not equal to n, then this quantity is never 0, right? Because this is the twice the sum of the first m integers, and this is twice the sum of the first n integers. So obviously, this is never not 0 if m is not equal to n. So therefore, this will imply that integral of pm times pn from minus 1 to 1 is 0. So thus pm and pn are orthogonal. Okay, so that's great. And so this was easy. And next, let's find the norm of pm. So that is more clever. It needs a more clever argument. So it only remains to show that norm of pn square is 2 upon 2n plus 1. So we need some intermediate steps before we can show this. So let's denote by d the differential operator d by dx. And let us first note that for I strictly less than n and greater than or equal to 0, di of x square minus 1 to the n. So this differential operator, so I'm applying this differential operator I times on this function x square minus 1 to the n. So this function is a polynomial, and I'm applying this differential operator d by dx I times to this. So the net result is going to be a polynomial, and I'm going to evaluate that polynomial at 1. And my claim is that we are going to get 0. Okay. So let's see how to prove this claim. So the proof is fairly easy. The difficult part is to make this observation, make this clever observation. So let's see. So this is clear once we observe that. So this is di x square minus 1 to the n. So this, so let me just put a bracket over here for emphasis. So this x square minus 1 to the n, this I write as x minus 1 to the n into x plus 1 to the n. And this x plus 1 to the n, that I write as 2 plus x minus 1 to the n. Okay, that is what I've done over here. All right. And then I expand this term out. So let me say expand using the binomial, right? So then that will become, okay, so let me just erase all this so that I can write a bit more clearly. Right, so when I expand, so I'm going to first, so when I expand this, what am I going to get? I'm going to get 2 to the power n plus n choose 1, 2 to the power n minus 1 into x minus 1 plus and so on, right? So that's what I've done over here. So, and this thing has to be multiplied with this. So we get this. So this is the first term. There's some constant is going to be there into x minus 1 to the n plus 1. So this x minus 1 to the n, this term over here gets multiplied with this guy over here, and we get x and so on, right? And let's see. Oh, okay, so I have, yeah, okay, so I mean to say, so yeah, so this is this. So when I open this up, so when I evaluate this polynomial at 1, yeah, so this differential operator, this I is strictly less than n, right? So this differential is going to get, you can just sum it, right? 2 to the n into x minus 1 to the n plus di into some constant into x minus 1 to the n plus 1 and so on. And all these I'm evaluating at 1. But now since I is strictly less than n, all these polynomials will be divisible by x minus 1. Right? So therefore all of them will be 0. Yeah. So, I mean, the proof is really simple. So let's go ahead. So by the same reasoning, we get that for I greater than or equal to 0 and strictly less than n, this di x square minus 1 to the n at minus 1 is also 0. Okay. So now let's look at the polynomial of degree n given by dn x square minus 1 to the n. So it's obvious that this has degree n. So once again, maybe I should have put an extra bracket over here, yeah, because this polynomial has degree 2n. And we are applying this differential operator nth order, like d by dx to the power n, so that the degree will drop by n, and we will remain with a polynomial of degree n. So we are looking at this polynomial. So let me erase this just for clarity so that you can see clearly. Okay. So for k strictly less than n, let us consider this integral. So pkx into y times x. So this is, yeah, okay. So by the definition of y, so here I'm just substituting the definition of y of x. So this is y of x. And this is just by definition of y of x. Okay, so let's go on. Applying derivative transfer with f equal to dn minus 1 x square minus 1 to the n and g equal to pkx, we get. So notice that, so this I'm taking to be my g, and this entire term over here, this entire term is d times f. And notice that f of 1 is 0. That's what we just saw. And f of minus 1 is 0. right? So we can apply derivative transfer and we will get, so this thing over here is, we have a minus sign, f, so this is f times dg, this is dg. Okay, now we do this again. So this thing now, this new thing, so let me just erase this. So we, okay, so I hope it's clear how we obtained this. I hope it's clear how we obtained the equality of these two. And let's look at this equality now, right? So let me erase everything. So to look at this equality, so this term again, this I will write as d times dn minus 2 into x square minus 1 to the power n. And now I will take this to be my f and this to be my g, right? So this integral is integral g df, right? And once again, by what we saw, this n minus 2 is strictly less than n, and therefore f of 1 is 0, f of minus 1 is 0, right? So we get a d square, yeah, so we get dg, which is going to be d square pkx times dn minus 2, right? And now all the i's which appear here are going to be less than n, so we can keep applying it repeatedly, the same process. So what we will get is, yeah, I think there will be some, there's a typo here, there will be some minus 1 to the power something, and after we apply it sufficiently many times, I mean we can apply it n times, so this will become dn pkx into x square minus 1 to the n. But notice that pkx is a polynomial of degree k, right? Pkx was our Legendre polynomial. So, and when I differentiate it n times, I'm going to get 0. So, okay, I have explained this. Since pk is a polynomial of degree k, we get that dn pkx. Okay, so this means that all these integrals, I mean, y of x integrate with pkx is 0 for all k. Okay, but this forces that y of x is equal to c times pn x for some non-zero constant c, as we know that pk's are orthogonal to each other. But here we have to, yeah, so the point is that, so yeah, so let me, I think I should add to that exercise earlier. So I had given an exercise earlier. That's a crucial observation. Yes. So p0, p1, p2 is a basis for p of x. Moreover, in fact, you will have to use this to prove that there is a basis. Any polynomial let's say q of x of degree less than equal to m can be written as is a linear combination of p0, p1 up to pmx. Okay, so when you try to, so earlier I had mentioned only this exercise. Okay, but when you try to do this exercise, this second part will also be immediate. In fact, you will have to use this second part to do the first part in doing the first part. Okay, So this is a nice and cute exercise. So I would encourage all of you to do this exercise. And the point is, so let's apply this exercise over here in our situation. So y of x has degree n. So this implies y of x is a0. There is an expression for y of x in terms of a0 plus a1 p1x and so on. Plus, and we only need to go up to pnx. From an plus, these terms are not going to appear because of this exercise. Okay, we know that there is a unique expression because p0 p1 up to p0 p1 dot dot, this is a basis. And the point is that if we take a polynomial of degree n, then then its expression will be in terms of p0 p1 up to pn. And now we have already observed that the inner product of y with pk's for k strictly less than n is 0, which means that all these is, okay, let me say a0 is going to be 0, a1 is going to be 0, and so on. So therefore, this forces that y is equal to some constant times pn of x for some non-zero constant c. As we know that y of x is a non-zero polynomial. It has degree exactly equal to it. Okay. So okay. So now this is our, by definition, our y of x, and we are evaluating y of 1. So once again, we just do the same trick that we did earlier. So this we write as dn and dot dot dot. So yeah, so when we differentiate this n times and we evaluate 1, we get we only this term is going to remain, right? We only need to consider dn 2 to the n into x minus 1 to the n, but this is equal to d by d the n times 2 to the n x minus 1 to the n, which is exactly equal to 2 to the power n times n factorial. So that is how we have evaluated y of 1, and these terms are going to be 0 when we evaluated 1. Okay, so that's great. So thus we can normalize our Legendre polynomial so that pm of 1 is equal to 1. Okay, so that is, we can take pmx to be equal to 1 upon 2 to the n times n factorial into this dn of x square minus 1 to the n. Okay, so I hope this is clear. So yeah, so in other words, I'm saying, so the solution to a differential equation, we can scale it, and that will also continue to be a solution, but we scale it in such a way that at 1 it takes the value n factorial into 2 to the power. So we will take this, yeah. So this polynomial pm of x, it satisfies the Legendre equation for p equal to m, and it also satisfies pm of 1 equal to 1. Okay, so great, let's go ahead. This is called Roderick's formula, and this is a very nice formula. In your tutorial sheets, there will be several exercises which are based on this. So, and we have just seen a proof of this formula. So now let us use this formula to compute the norm of p and x. So integral p and x. So yeah, so norm, to compute the norm square, we have to take p and x, we have to multiply it with itself and integrate from -1 to 1. So I have just, this is the coefficient, and there's going to be from -1 to 1. This is just the definition. I've just written the definition. So you can just go back to the previous slide. So I just, okay, I'm sorry. This should be pn, I think. Yeah, maybe I should. Okay, so this I've just substituted the definition. And now, yeah, I have made this very quick transition. So yeah, so, but if we think about it for a minute, it should be clear now. So I'm applying derivative transfer. This I'm taking to be d times f, and let's say this is my g. And what is f? F is d to the n minus 1 x square minus 1 to the n. But we have already seen many times now that f of 1 is equal to f of minus 1 is equal to 0. Okay, so I can keep doing this, and yeah, so by derivative transfer, by repeatedly doing that, we will go from here to here. I will leave it to you to figure out what we are doing. If yeah, it's, I mean, it's trivial if you have understood what is happening so far. And okay, so then, okay, so this we have evaluated. So that's just, we just get a 2n factorial. Okay, this minus 1 to the n we take inside over here and absorb it. So this becomes this. Okay, so that's great. Okay, so now we denote this integral by I of n. This integral we denote by I of n, and we will get a recursive formula for I of n. Okay, so that is our strategy. So how do we do this? So we look at I of n. So by definition, it's minus 1 to 1 integral from minus 1 to 1, 1 minus x squared to the power n dx. So this I can write as minus 1 to 1, 1 minus x squared to the power n dx by dx. So this is derivative of the function x dx. So once again, we are going to use derivative transfer, I hope. Am I doing that? Yeah, I have done derivative transfer. Right, so this is my f now. This is my f, and this is my dg. So g is equal to x. Right, and f of 1 is 0 and f of minus 1 is 0. So we can apply derivative transfer. So yeah, so when I, so this is going to be minus, okay, so when I apply, yeah, when I apply derivative transfer, this is going to be equal to, this integral is going to become minus of integral minus 1 to 1 df by dx times g dx. And when I differentiate f, I'm going to get 2n, and the minus sign is going to get cancelled with this minus sign. So we get exactly this. So let me erase. Yeah. So let me erase this, and you can convince yourself that this step is okay. Yeah. This is by derivative transfer. F is equal to 1 minus x squared to the power n, and g is equal to x. Okay. And now this term, this x square, I can write this x square as x square minus 1 plus 1. Right? And then I immediately get this formula. Right? I can break this bracket as x square minus, when I take the x square minus 1, I get minus 2n in, and the 1 will give rise to a in minus 1. So I immediately get this. So therefore we get this recursive relation. Yeah. So we take, yeah, so I mean, we have gotten I 2n is equal to minus 2n in plus 2n in minus 1. So we take this to the other side and we get this. 2n plus 1 in is equal to 2n upon in minus 1. And we conclude that I sub n is equal to, okay, yeah, so this. And we conclude that a norm, I should have written norm square, I think. Norm square is this factor over here times I of n. So that is this factor over here times I of n. Yeah. I of n is this thing. And I of 0 is just integral minus 1 to 1 dx, which is 2. Right. So this completes the proof of the theorem. Okay. So let's pause for a few seconds. So this was one of the nice theorems whose proof we will see. There will be very few theorems whose proofs we will see. But yeah, this is one of those few theorems. Okay, so let's go ahead. These are some exercises for you. Okay, this is a more general exercise. Yeah. So recall the proof of the Ganishmir orthonormalized process, and this is the exercise I gave. So let fi be a collection of non-zero polynomials. Assume that fi x has degree I. Show that f0 up to fn x is a basis for the vector space consisting of polynomials of degree less than equal to n. Yeah. So yeah, exactly. So we have about 20 more minutes left. So let's go ahead. Okay. So let's just recall what we have done so far. So the Legendre equation is given by this so that depends on a real number p. P belongs to real numbers. And when p equal to m is an integer, then exactly one of the two independent solutions is a polynomial. And this polynomial is denoted by pmx. This is a polynomial of degree m. So here m is greater than or equal to 0. When m is greater than or equal to 0. Okay. So, and this is the theorem that we have proved just now. We have proved that Pm and Pn are orthogonal to each other if m is not equal to n, and their norm square is 2 upon 2n plus 1. And so here there's also this condition that Pm 1 is 1. I should also state this normalizing condition. Yeah. So this is the theorem which we have just proved. Okay. Expansion. Okay, so let's just go through this also. Expansion of polynomial in terms of Pn's. Since each Pn is a polynomial of degree n, we see that P0, P1, P2 form a basis for the vector space of polynomials P of x. Okay. If f of x is a polynomial of degree n, then we can express f of x is equal to summation k equal to n to 0 to n ak pk x, where ak is a real number. Okay. To find ak, we can use orthogonality of the Pn's. So we integrate f to find ak's. So yeah, right. So integral f x pk x dx is equal to integral minus 1 to 1. Here I have just substituted this value of f, and the pi's are mutually orthogonal, so only one of the terms will remain, and that's going to be ak times minus 1 to 1 pkx times pkx. So therefore we can, yeah, so this is the answer. So these coefficients a k's, they can be found out like this. Okay. So all this is straightforward. Okay, so now we come to, yeah, so now we come to a sort of point in our course where this is, I suppose, going to be something new to all of you. And this is, yeah, I don't want to explain too much, and I just want to give you a idea as to how this works. So square integrable functions. So, I mean, really, if I have to do this properly, then you would have to take a course in measure theory. But obviously, we are not going to, yeah. Okay, so a function f of x on minus 1 comma 1 is square integrable if I integrate from minus 1 to 1, I take f of x square, and this integral is finite. Okay. For instance, polynomials, continuous functions, piecewise continuous functions are square integrable. So many functions that we see are square integrable, but many are also not square integrable on, let's say, on the interval minus 1 to 1. So the set of all square integrable functions on minus 1 comma 1 is a vector space and is denoted by L2 minus 1 comma 1. For square integrable functions f and g, we define their inner product by f comma g is equal to minus 1 to 1 f of x g of x dx. So you see already it's like non-trivial, right? So here, what is the claim in this sentence? The set of all square integrable functions on minus 1 comma 1 is a vector space and is denoted by L2 minus 1 comma 1. So if I take square integrable functions, it's clear that I can multiply them with a scalar and the scalar remains square integrable. So in other words, if I start with the f, which satisfies this condition, and I multiply f with lambda, then the new function also satisfies this condition. But it's not so clear that if I take two functions f and g, such that integral f square, so this is minus 1 to 1, dx is finite, and integral minus 1 to 1 g square dx is finite. Then the integral minus 1 to 1 f plus g whole square dx is finite. Right? This is not so clear, right? I mean, it will need a proof. And yeah. So yeah, so so this is something worth mentioning. So already we have used something non-trivial. Okay, but let's assume this. So we can, if we take square integrable functions, then we can multiply them with scalars and add them, and we will get square integrable functions. Okay. Now, so great. So now we have a vector space of square integrable functions. So on this vector space, we define an inner product. So this is the inner product we define on this vector space. Okay, and yeah, so once again, to define this inner product, we need to check a few things, right? We have to say that, suppose I'm given square integrable functions f and g, which means f and g satisfy this condition, then this thing is actually a real number, right? It should not happen that, okay, f and g satisfy this nice property, but when I multiply them and integrate them from minus 1 to 1, I get something which is infinite. So we have to say that. Okay, great. So once we say that, it's clear that this thing is symmetric, because inner product of f and g is inner product of g and f, and it's, yeah, well, let me say it's clear that inner product of f comma f is greater than or equal to 0. That is of course very clear, but and also that if f comma f is equal to 0 if and only if f is equal to 0. So let's say if f is a continuous function, then this is clear. Okay, so I'm going to cheat enormously when I talk about square integrable functions, but I will tell you what the main point is. Okay. Okay, so the Legendre polynomials no longer form a basis for the vector space L2 minus 1 comma 1 of square integral functions. Okay, so they don't form a basis for this vector space. Yeah, so this vector space is huge. So where am I making? Yeah, in fact the space L2 minus 1 comma 1 is huge in comparison with the space spanned by Legendre polynomials. So the space spanned by Legendre polynomials is exactly all polynomials. This space is exactly all polynomials. Right? So when we take the space L2 minus 1 comma 1, it contains enormously many more functions, right? I can just take any function. I can just take something which is 0 and then it bumps up, or I can take something which, I can cook up as many horrible functions as I like. And obviously those are not going to be polynomials, right? Because this function, this has infinitely many zeros. It's 0 in this interval, in some interval over here, and a polynomial can never be such a function. So what do we mean by huge here? So I will end with this slide. So the set of I will only give a sort of a very heuristic answer to this. So the set of rational numbers is contained in the set of real numbers and is dense. Yeah, so dense means I have my real line, and if I take any real number and I take any neighborhood which is very small, no matter how small, then I can find a rational number inside that neighborhood. Okay. Now to make sense of the small, I need a norm on the real line, right? What do I mean by small? It means that the, okay, so let's imagine that we are going to zoom into this picture. So this is my x naught and my interval looks like this. So to say small interval, it means that this length of this interval is epsilon, right? So we need a notion of length. So yeah, so what I'm trying to say is, to use this word dense, we need a notion of length. So yeah, because to say dense, I have to say that any small neighborhood of x naught contains a rational number. And to make sense of the word small, I need a notion of length. And on real line, we have an obvious notion of length, which is the distance. So what I want, yeah, okay. So however, the size of R is much larger than the size of Q. So the real numbers is an uncountable set, whereas the rational numbers is a countable set. So I don't want to go into this at all, but these ideas were formulated precisely by George Cantor. I'm not sure if you have encountered this, maybe in your MA 105 course or something, the first course that you have taken on analysis. Okay, so in the same sense, like just the way the rational numbers inside the real numbers, rational numbers is a very small set, but still every real number can be approximated by rational numbers. In the same way, these Legendre polynomials form maximal orthogonal set in L2 minus. So, I mean, this is not the statement that I want to make. I want to say that in the same way, every function in L2 minus 1 comma 1, we can approximate it by Legendre polynomials. So what do I mean by that? So this means that a square integrable function which is orthogonal to all Legendre polynomials is necessarily the constant function 0, a non-trivial fact. Right. So this statement has to be taken with care, because let's take a function. Okay. Right. This is -1. This is 1. Right. So let's take a function which is 0 everywhere, except let's say at half. At half, I decide to say that this function is 1. So this is my coordinate system. At half, I decide to change the value of this function, and I say this is 1. And it's 0 everywhere else. So f of x is equal to 0 if x not equal to half, and 1 at x equal to half. Right? So now let's take f of x on -1, 1 on this interval. And now let's just integrate -1 to 1 f of x with pkx dx. So obviously this integral will be 0, right? Because this new function, it will be 0 everywhere and just at just one point. So obviously when if you have a function like that, the intuitively integral means area under the graph. So the area under the graph is 0, right? But this function is not the 0 function, right? It's not identically 0. Yeah. So however, in L2 minus 1 comma 1, this function is 0. So I suppose this point may be, as I said, I have not defined L2 minus 1, 1. So I don't want to explain this anymore, but yeah. Yeah. So f is equal to 0 in L2. Let me just use this term, minus 1 comma 1. So the meaning of this is, meaning of this is f is 0 almost everywhere. Okay, so I will end the lecture today, and yeah, I can take questions, but if you're going to ask me questions about the space L2 minus 1 comma 1, I'm not sure how satisfactorily I will be able to answer that. But anyway, yeah, so we can take questions now. I will end the class right now. Otherwise I will. Okay, there is okay, for some reason there were many chats which did not appear, so I don't know why. So let me try to take them one by one. Okay, I don't know. I'm sorry, I missed several questions. Somehow it did not show up in chat, so I thought there are none. So please explain again why A0, A1 are 0 on slide 24. Okay, so let's go to 24. A0, A1. Oh, okay. Right. So yeah, I can explain this. So I suppose your question means, uh, so let's see. So we have concluded that integral minus 1 to 1 y of x pkx is equal to 0 for k strictly less than n. Okay. On the other hand, we also know that y of x, since y of x is a polynomial of degree n, this can be written as a0 p0x plus dot 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 plus an pnx. Okay, this is using the exercise. So you have to do the exercise and then you will realize it's true, right? Now, how do we compute the coefficients ai's, right? So to compute the coefficients, we will multiply both sides with pkx. Let's say yeah, let me just multiply both sides with pkx, right? So on the one hand, I will get, on the left hand side, I will multiply both sides with pkx and I will integrate it from minus 1 to 1. So on the left hand side, I will get y of x pkx, and on the right hand side, I will get a0 integral minus 1 to 1 p0x pkx plus a1 minus 1 to 1 p1x pkx, and so on, right? But now notice that all these p0 pk, p1 pk, these are all 0, the integrals, because we have already shown that the pi's are mutually orthogonal. Okay, so therefore only ak will remain. So this is what I had done earlier. So this is going to be, so this integral will now become ak into integral minus 1 to 1 minus 1 to 1 pkx whole square dx. Now this quantity is non-zero. We computed the norm square earlier. And this quantity is 0 because k is strictly less than n. And that's what we just proved, right? That implies that ak is 0 for k strictly less than n. Okay, so I hope this is one question. I hope this clarifies. If you could change your name, this person, so then I could, yeah. Anyway, so let me take the next question. Could you please explain again why we are taking the subsets minus 1 comma 1 only? Well, there is yeah, I mean, I don't know, that's just the nature of things. I mean, I am only taking this subset. I mean, if you want you can okay, let me erase this. sorry, let me start a new page over here. Oh my god, where's it gone? Oh, oops. Okay, so I mean, it makes, you can take p of x is equal to vector space of all polynomials, and you can define a new inner product as follows. You can take a and b, and you can define f of x, g of x. This, you can take this as the definition of f comma g. This makes perfect sense. So I mean, depending on what you want to do, depending on the theorems you want to prove, you will choose your a and b appropriately. So I don't really have a, yeah, I don't really have an answer to this question. Could you explain again why we are taking the subsets -1 to 1 only? I mean, depending on what we want to do, we have to choose our subset appropriately. Okay, I hope that answers Gopal's question. So let's see. Someone has written in slide 24, y of x can also be a linear combination of other pk and not just equal to c times pn. This is something which I just explained right now. Someone else has also answered this question, asked this question. So I hope this is clear to that person also. Okay, thank you. Yeah, if it's not clear to people, then I can, because well, Piyush has answered a question, because our coefficient of y double dash was 1 minus x square, so we are well, it definitely, but that is not Gopal's question. I mean, yeah, but polynomials p of x are defined everywhere. They have a radius of convergence infinite. So I mean, Gopal's question is, yeah, I don't think Piyush's response is going to satisfy Gopal. So I mean, that's my guess anyway. So let's see, let's look at other. Someone has written a message. We wanted to communicate this request from students. Could you please upload the PDFs of the annotated slides instead of the XOPP files? Okay, fine. I can do that. Yeah. I think for lecture 2, I had uploaded the PDF as well, but maybe for lecture 1, I did not do that, but in future I will do that. Thank you for letting me know. On slide 19, should the orthogonal be replaced by maximal orthogonal? Let me just check. Slide 19. So let's see. Let's go to slide 19. Well, on slide 19, maximal orthogonal and orthogonal, the word maximal will not add anything, because we already know that P0, P1, P2 dot 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 is a basis for P of X. So yeah, no, so slide 19 is good as it is. The word maximal orthogonal is used when we have an orthogonal set which is not a basis. On this slide, however, this orthogonal set is a basis for the space of polynomials. So I hope this answers Utkarsh's question, if he's still around. Any other questions? Yeah, I mean, let me reiterate once again. Let me try to explain this once again. And what is the, let me give some context to it. So when we have a finite dimensional vector space, when V is finite dimensional, this is the best situation, best possible situation. Yeah, then all theory and everything works well. Now let's consider a situation where V is infinite dimensional. Right? So in this case, we can always cook up a basis. So this is, once again, someone had asked me this question, right? Can we have a maximal orthogonal, can we always have a maximal orthogonal set? So right now there is no inner product, so V is just a vector space. So we can always cook up a basis. We can always take these VIs, right, by axiom of choice, let's say using Zorn's lemma. Yeah, I mean, roughly, what is the argument? The argument is that, okay, if I will take some set v1, then is span of v, is v spanned by all of v1? No, then there's a vector outside this span, so then I will add v2. Then I will ask, do v1 and v2 span all of v? No, then I will add a v3, and so on. Now, at the end of the day, so the Zorn's lemma or axioma's choice will tell us that we can choose. It's an assumption that we can choose a basis. So yeah, I don't want to go into this, but now let's come to V is infinite dimensional inner product space. Okay, so here we may have a very small set, like in comparison to the size of V, V1, V2, and so on. So when we take an infinite dimensional vector space, well, for instance, L2, the set of bases will not be countable. It will be some huge set. It will be some VI's, yeah, for I belongs to some index set I. So when we have an infinite dimensional inner product space, we can have a small set, V1, V2, and so on, indexed by, let's say, integers, such that the VI's are mutually orthogonal. And every vector V, and if V comma Vi is equal to 0 for all I, implies V is equal to 0. But this does not mean that Vi's is a basis for V. Okay. So this is the point I was trying to emphasize. Anyway, we will take this up more in the next class. So are there any other questions? Sir, can you explain last two steps of slide 25 again? Okay, so let me go to slide 25. So let me go to slide 25. Sorry. This is Roderick's formula. Okay. So what is slide 25? Okay, yeah. Okay, great. So, okay. So when you say last two steps of slide 25, do you mean the computation of this integral I sub n, or do you mean before that? Is Piyush around? Okay. Last step in this slide. So, okay, so let me just clean this up a little bit. Okay, so let's see what we are doing. So let me add a page. So what we have is, we have this integral I n, this integral minus 1 to 1 minus x square to the n dx. Okay, and our aim is to compute the value of this integral. Okay. Okay, so what we do is take f equal to 1 minus x square to the power n and g equal to x, right? Then in is equal to integral minus 1 to 1 f times dg by dx, right? This is obvious. Okay, Now, remember what was derivative transfer? We wanted that fg, we wanted fg of 1 minus fg of minus 1. Oh, sorry. Minus fg of minus 1 is equal to 0. If this happens, implies integral minus 1 to 1 f dg by dx, I mean f, yeah, is equal to integral minus 1 to 1 minus of this df by dx times g dx, right? But here we have that f of 1 is equal to f of minus 1 is equal to 0, right? So therefore this condition applies. So from this we can say that, so this implies that in is equal to minus integral minus 1 to 1 d by dx of 1 minus x square, I'm sorry, 1 minus x square to the power n times x dx, right? But what is this? This is minus 1 to 1 2n into derivative of this, that's 1 minus x square, I'm sorry, let me just slow down. So this is n into 1 minus x square to the n minus 1 into derivative of this 1 minus x square, which is minus 2x into x dx, right? Which is equal to 2n into integral minus 1 to 1 1 minus x square to the n minus 1 x square dx. But now I write this as 2n into minus 1 to 1 1 minus x square n minus 1 into x square minus 1 plus 1 dx, and this is equal to 2n minus 1 to 1 minus 1 to 1 1 minus x square, so there's going to be a minus to the power n plus 2n into integral minus 1 to 1 1 minus x square to the n minus 1 dx. So this is equal to minus 2n times in plus 2n times in. Okay, I hope this is clear now, Piyush. So now you can read. Okay, yeah, that's our aim. We are computing in recursively using integration by parts, right? Okay, are there any other questions? Okay, so if not, I will end the recording and we will stop the class.